during the lunch. So let's thank the speaker once again for the wonderful talk. Our next speaker for this session is from University of Barcelona.
Chapters here. First, the title belongs to the University of Barcelona and also to the University of Barcelona. Then, very important to predict behavior of a well, to predict hydrological processes, for practical things. Essentially, medium is disorder, okay? And as a function of pressure, as you lower pressure, which are typically this process, oil is low. Yes, it is changing the profile of the pages. So they are like, okay. If instead of that you would do a smooth or a profile glass with copper patches, okay, and we take pictures from above, we can incline the cell with an angle alpha for reasons that I will explain, and we can drive the fluid, in that case silicone oil, by two means. One, with this reservoir that allows to impose a constant pressure to the system, and by raising and lowering this reservoir, we can change the pressure, the applied pressure, or we could use a syringe pump, and then this would be flow rate control. But for the moment, let's just stick to this quasi-static pressure driving, okay? Well, in that first experiment, we used just one single patch of copper. Is this one shaped here? It has sharp edges, as I said, a width W, and we are driving with constant pressure. As you see, this is seen from above, right? What we are interested in is in the deformation of the front as it enters the patch. Okay. Essentially, now I come to your question. The interaction with the patch, this is the copper patch, is a very tiny perturbation of the gap thickness of the cell, is through the modification of the curvature of the meniscus. In that case, this is oil, so this is wetting the glass plates and the fiberglass. So this has this curvature, but this curvature gets larger, okay, when it enters the patch. So what we have with a variable gap thickness Hilly-Shaw cell, which I call an imperfect Hilly-Shaw cell, because of those imperfections, is quite complicated. There are several mechanisms that occur at the same time. In a locally smaller gap, like this one, first you have a reduced permeability. There is less space, the fluid is more confined, so the permeability is smaller here. In principle, the decrease in permeability will slow down the fluid, right? But there is mass conservation, and because the space is limited now, the front will speed up to conserve mass. So this is counteracting. And then there is another mechanism to pull ahead the front, which is the dominant one, but all the three are important, which is the capillary. There is a pressure jump across a curved interface, as you well know, okay? But this pressure jump is more important. The more important is the curvature of the meniscus. This is the Young-Laplace relationship, right? So this is feeling a kick in pressure towards invading the patch here. This is the mechanism of the invasion. Now we go to the experiments. This is a view from above. Silicone oil on the left, air on the right. Okay, we have a little inclination of the cell. And now this is not very visible, but this is the defect. You see, the moment it touches, it deforms the front. Oil is here, air is here. And you see this is plot here, the deformation at the center line acquires a steady value all the way until it reaches the other end. And at this other end, the behavior is very different. It gets pinned here until the whole interface is flat. So you see, the way of the pinning here is very different from the abrupt jump at the entrance. Now this is leaving the defect in that linear form. Now the other way around. Now we drain. Okay? We remove the oil by lowering the pressure at the entrance. Well, you can see that on the right edge, the situation is perfectly reversible. The front has been pinned here until it adopted this curvature. And then the steady state is nearly recovered. Okay? And things here are very different. The front gets pinned by just one point at the edge of the defect, here. And now it drops and recovers flatness. Okay? So this forms an elementary hysteresis cycle. We see like an elementary ingredient for what will be the macroscopic hysteresis of the system. The entrance of the front to the defect is irreversible and totally different from the exit of the front from the defect. Right? So to understand that, we try to, this is just a collection of pictures that explain better what I just said. You can see that this part of the problem is totally reversible, so the collection of fronts in that direction is exactly the same as the collection of fronts in that other direction in drainage, but not at the left side of the constriction. At the left side of the constriction, the deformation was produced just when the front touched in imbibition, and flatness was only recovered when the last point of the front detached from the defect. So this hysteresis cycle was formed. Okay, now can we understand that? We try to write down a theory for that problem based on the pressure across the interface. So delta P here is the pressure across the interface, right? And we call this the elasticity of the line, but it contains several contributions. The pressure across the interface would be given first by this term, which is the linearization of the Young-Laplace expression for the capillary pressure jump. So instead of taking the full curvature, which is highly nonlinear in H, in eta here, the deformation of the front, we just take the first order approximation, which is the second derivative. And this keeps the equation linear. And this is surface tension. Then the next contribution comes from the viscosity contrast across the interface. Because of the viscosity contrast across the interface, the pressure gradient changes at the interface, and this produces this extra pressure term, which is again proportional to the deformation of the front. The last contributions is hydrostatic. Because our cell is inclined, we have an effective gravity GE, which is G times the sine of the inclination angle, which times the difference in density gives another contribution to the pressure difference, because the densities of the two fluids are not the same, right? So with all these three contributions, we have the linear contribution to the pressure jump across the interface. And we collect all those terms here in this linear operator calligraphic L times eta, right? Now, the capillary pressure produced by the out-of-plane curvature, so the one we were discussing before in the perpendicular direction to this picture, okay? Well, this is given by the out-of-plane curvature of the meniscus, as I said. We put it as an additional ingredient here, which acts as the disorder. So this is the perturbation. We have this linear system, we perturb it with this, and we see how it responds, okay? So this, in mechanical equilibrium, when forces or pressures are balanced, we will have this all the time. We are driving the system quasi-statically. So at every point, we achieve quasi-static equilibrium, right? We achieve mechanical equilibrium at every point in the driving, so we can write down this equality here. And then because L is linear, we can use the this convolution integral, or if you want the green function formalism, to understand what the resulting deformation will be when the defect is extended in the x direction, okay? And you can make the calculation using this expression here, and you obtain that the green function for that problem is this expression here. A characteristic length, which is actually the capillary length of this problem, surface tension divided by the gravitational term, right? Divided by 2 times the surface tension and this exponential which decays with distance. So this is telling us that the perturbation is maximal here and decays with the coordinate x in both directions, according to this propagator here of the perturbation, right? Okay. Now, if we apply that to a localized Mesa defect, a Mesa defect has this stable shape that we were using with sharp edges, okay, then this term can be computed very easily because the pressure is constant all over the defect, so we take it out of the integral, PA, and what is left here is a sort of a spring constant. So this is telling us that the front is acting as a spring constant, trying to remove the perturbation produced by the defect, right? And this spring constant, if you want to call it like that, in this linearized problem, is given by this term, which depends, of course, on all the system properties. The width of the defect, the capillary length of the problem, the surface tension. All the ingredients that actually damp the perturbations of the front. PA for this Mesa defect is just, can be approximated by that because this is just the surface tension divided by the first approximation to the curvature. So we plug it here, and the first thing we see is that PA depends on delta B. So if delta B, which is the thickness of the patch, how much it reduces the gap thickness of the cell, the copper patch. If delta B is positive, PA is positive, and this is what we have been seeing. The constriction is attractive. So a constriction attracts the front. But if PA is negative, because delta B is negative, so we have a hole in the cell, an expansion in the cell, then it is repulsive. In the repulsive case, the left side of the defect and the right side of the defect are reversed. So you would have reversibility on the left and hysteresis on the right. And this we checked in the lab. I will not show it, but we check it and it works perfectly fine. It's in that publication here in PhysRep Fluids. So we understand what's going on quite well, okay? And then where the hysteresis comes from? Where does it come from? Well, I repeat now what I already explained, but putting all the terms together. This is now the disorder introduced by the out-of-plane capillary pressure of the copper patch, okay? These are the other terms that we are familiar with. I removed the term dependent on velocity because we are driving the system quasi-statically. So we look only for the equilibrium configurations given by this pressure balance, PE equals 0 here. And I can derive this through this plot. This plot, this linear straight line, these straight lines that are represented here represent all the linear terms, the first 3 terms here, okay? This move because the pressure is being increased, so it changes from this to this, from this to this, etc. The other profile that you see here is the profile of PC for a Mesa defect. It is this table-shaped profile for the out-of-plane capillary pressure. Now what happens is that the equilibrium positions are given by the crossings of these lines with the PA profile. But you can see that on the left edge of the defect, the left side of the defect, there are 3 crossing points when the interface approaches this. Well, it turns out that 2 of them are stable equilibria, they are minima of the free energy, and 1 is an unstable equilibria, it's a maximum of the free energy. So this is a 2-well problem in energy, okay? And actually what happens is that as the front approaches the defect, even though here the other state already exists, it exists only in metastable form. So its energy, it's higher than this one. So the system remains flat. The interface remains flat with zero deformation. And only when it touches the defect, then it finds the other solution. This becomes unstable. The system jumps to this new solution, and this is this abrupt jump ahead here of the deformation. Now, we follow the evolution here, and then, of course, there is only one crossing point here between the inclined lines and the pressure profile of the defect. So it means that there is only one possible equilibria, and this is exactly what the system follows. This was in imbibition. Now if we retrace, the path here is exactly the same that we had, as the experiments prove, because there is only one crossing point. But not here. Here, when we arrive to that point, somewhere here, the system already has another possible solution, but this is of higher energy than this equilibrium position. So the system remains trapped in the deformed state, okay? And only when it reaches this point, it cannot be trapped anymore there. This minima becomes unstable, and then it suddenly jumps to the undeformed state here. And this is the red jump here at the other side. And of course, this behavior produces this hysteresis cycle. Okay. To be honest, I must say that we got the inspiration from that, from the very well-known paper by Joanny and Degens, 1984, on the hysteresis of contact lines, the wetting problem. Okay. It's the same physics. It is the same physics, except that the contact line has an extended medium behind, etc., which is not the case here. So we have to adapt it to our problem in the Hilly-Shaw cell. Now, another prediction, we understand the hysteresis cycle. Can we understand the steady state deformation of the front? Well, in principle, this equation would predict you what the steady state is if you impose mechanical equilibrium. Okay? And then I haven't written the equations, but the prediction is that this complicated expression here, plotted as a function of the capillary length versus the gap thickness squared, should give an identity, okay? Should give this dashed line here. Here, you see the experimental results for a series of experiments that we did with different defects, different inclinations, different configurations of the system, okay? We worked hard on that, but I think the results are quite reasonable. I mean, they represent quite accurately the expected behavior. Deviations are mostly due to nonlinearities. So to the fact that we approximated here the capillary pressure term in the plane of the cell by its linear approximation, by this second derivative. Okay. Good. I turn now to the macroscopic scale. Okay. Now there are two people that appear in a scene, which are Ran Holzman from Coventry University, you might know, and Marco Dens, also from Barcelona, but a different institution, and Hydrological Institute of Research, IDAEA, from the Spanish Council of Research. Okay. Well, we got to know each other through our common interest in hydrological problems and porous media problems, and we decided that what we had seen for an individual defect could be extended to a fully disordered system to our imperfect Hilly-Shaw cell, as we call it, imperfect Hilly-Shaw cell, which now contains many copper patches. Here you can see them. Okay? This is the movie we saw before. Indeed, it reproduced quite well the imbibition of coffee. So how can we go from the previous knowledge to that macroscopic behavior? Okay. This was our intention, to do this upscaling. Essentially, we write down the same equation that we had before, exactly the same, okay? But now it's a local equation for point x for an extended interface, which is h of x, which is able to go through many defects at the same time, okay? So h of x now, it's the interface, but it can touch, you see, patches of defects at many different locations. So actually PC is dependent on x and on h of x, because this is like a quench disorder. It is a quench disorder, which is only acting when the interface is on it. If not, it is not acting, okay? So again, we drive the, oh, sorry, mistake. I think I was here. No. Where am I? Yes. Now, good. So, interestingly enough, well, this is the expression of PC. Okay, cos theta is just the cosine of the contact angle, but we take it fully wetting because the silicone oil fully wet, so it's a 1 here. Okay, and then we realized that the equation we had derived was actually, for an extended front, the same as the equation for an elastic line in a medium with a quench disorder. And because we linearize the equation, this term here, it turns out that it is the Quench-Edwards-Wilkinson interfacial equation, because it's the linearized version of interfacial equations in disordered media. It can also be mapped to a random field Ising model, though a random field Ising model, you would write it in discrete variables, not in continuous variables like here. No? But I know that Subhadeep and Marco and Ran are working on this analogy to the random field Ising model, right? So to make the analogy stronger, you have to think that this mechanical balance, mechanical equilibria, is given actually by this functional derivative of a Hamiltonian with respect to the interface. Okay? If you write this in this form, you end up with realizing that you have a Hamiltonian problem with this Hamiltonian. The different terms in the Hamiltonian correspond to all the pressure terms you had in this equation. Okay. So, and then this, of course, is relatively amenable to computer simulation, and this is what we did. Our computer simulation used synchronous dynamics. So we discretize the x-axis in equi-spaced intervals. For any external pressure, we increase the local height of the interface by a little amount for all sides at the same time, but only for those that are out of equilibrium. So those that experience a pushing pressure ahead. They have this equation not equal 0, but larger than 0, so they are pushed ahead. And then we repeat that procedure iteratively until all points are in equilibrium. This we measure by a tolerance epsilon. So whenever this equilibrium is smaller than the tolerance, we accept that the system has reached mechanical equilibrium. Then we change the pressure, the applied pressure by a little amount, and repeat the whole procedure. In drainage, we just do the opposite, as explained here. And those are the results. So you see here, maybe I will have to pass it again. Here it is. You see, this is imbibition first. And this is the pressure saturation cycle that you obtain. And now you you drain the system. Okay, and this is it. Here we amused ourselves doing a partial cycle. So we stop drainage at that point, imbibe again, redrain, and drain forward to the end. I will pass it once more. This is because we wanted to check whether there was memory in this system. Notice that pressure increases downwards in this axis. This is a bit bizarre. And this is saturation of the wearing fluid. But now I want to show to you that this cycle returns exactly to the same point that it left, the drainage branch. This will be important. This exactness is exact to the minute consequences. So if you look at the configurations, you will see that they are identical. So now we have an interesting link between microscopic capillary physics, spatially extended collective events, Haynes jumps, which are the abrupt jumps that you see in the fluid displacements, and large-scale hysteresis as represented by this plot here. Now, we can play with the model, look for the impact of microstructure. So if you change, for instance, the diversity of the noise present in the system, the heights of the copper patches, this is difficult to do in the experiment, but simple to do in the numerical simulations, then you see that you can control the size of the hysteresis cycle. The wider the Gaussian distribution of heights of patches, the larger the dissipation, the hysteresis cycle, right? And then also you can play with gravity. So the larger the gravity, the more inclined is the hysteresis cycle, as you can see here. And interestingly enough, if you reduce gravity to 0, it's not plotted here, because when you make gravity equal to 0, the whole displacement takes place in one single step. So the system is unstable, and it washes the whole disordered medium in one single step. Okay, this is interesting, and it had been shown already by people in Norway, in PorLab, that this was the case indeed. Okay, so gravity plays an important role, and displacements become unstable in the absence of gravity. Now, let me, well, we use the single MESA defect just to verify our numerical code. We reproduce exactly the hysteresis cycle that we had in the experiment, so we were very happy with that. We had quantitative agreement without fitting parameters, so this was rather impressive to us. But then we wanted to focus on memory properties. So particularly in this partial cycle that we did here, you can see a typical property of disordered systems and a typical property of hysteretic systems. This is the multiplicity of possible metastable states. Because of the disorder, you have many, many possible states in which the system can feel happy in equilibrium. But how can you reach them? Well, here it is clear that for one given pressure, you have at least here 1, 2, 3, 4 different equilibrium states that you can reach. 2 of them are during imbibition, and 2 of them are during drainage. But they all are stabilized at the same pressure, which is quite amazing. And actually you could have many more. All inside this hysteresis cycle, there are metastable states that by doing complicated paths inside this hysteresis cycle you could reach. Okay. And you can see that those states are different. They are not the same. You can see here the actual configurations, interfacial configurations. This is IP, I primary. This is I primary, the lowest one. Of course, it's the lowest saturation. Then you have drainage primary here. It's the one with larger saturation. And in between these 2 others. Okay, I don't remember what the S stands for, but small or something, I don't know. But this is one for imbibition, the other is for drainage. You can see that they are not the same, although they exist at the same pressure. Okay. So can we explain that? Yes, we can, based on our our previous knowledge of the community on hysteresis in disordered systems. In particular, Jim Sethna from Cornell University showed that this had to happen in disordered magnetic media, in disordered magnetic models like the random Philizing model, in the absence of thermal fluctuations. Thermal fluctuations would destroy that, because we need a deterministic dynamics. We need something that it's deterministically obeying the mechanical rules, right? And I will try to explain that. It's a bit involved, but I will just sketch how the proof goes. The authorship is due to Karin Dahmen, Jim Sethna, and others. We adapted here to a model with continuous variables instead of discrete variables. 10 minutes, thank you. So the first thing is that the system must obey what is called Alan Middleton's no passing rule. So one front that is behind another, and it's driven by a pressure PR, which keeps always smaller than PS, will never overtake this other front S. So R will never overtake S, provided that PR is always smaller than S. This you can check with your dynamics, and it turns out that this is true for our system. You can prove it because of the different terms here, the curvatures, etc. You can check that the dynamics obey that. This is Middleton's no passing rule. It was derived for charge density waves long time ago. Okay. Then you need deterministic dynamics, but we do have deterministic dynamics. There is nothing random here. Okay. The quench disorder is still, it's random, but it's still time independent. So we have deterministic dynamics. Okay. And then we need rate independent dynamics, and the way we drive it quasi-statically ensures that there is no rate dependence at all in this problem. Okay. Well, these three properties together lead to return point memory. So this is the name of this memory property that we saw, that a partial cycle will return exactly to the configuration it had left the main branch from. Okay. And the reason is that you can go from this point to this point, okay, in the upper branch through two paths. You can take this path here and you go from 1 to 2. You can take this lower path here and go from 1 to 2. Okay? And actually you have followed exactly the same path, because this is the main imbibition, the main drainage path, sorry. But you can play by doing a partial excursion. And a partial excursion corresponds to these ups and downs here. This is this. Okay, here we do one, and then another one inside, and then another one. And then, because this trajectory is bounded by the two other trajectories, and the two other trajectories are actually the same, exactly the same, they are identical, okay? They are identical in this representation, then you are sure that you will return exactly to that point. And this is the return point memory, okay? And this is perfectly satisfied by our system, okay? And now, of course, it's interesting to compare with experiments. And experiments are difficult because you have to be very careful in driving quasi-statically the system. Students spend lots of hours doing it mechanically. Now we are trying to automatizing it. But this is the comparison. So the red line here is the result of the average of many, many, many numerical simulations with different disordered realizations. And the blue dots are the experimental results under the same experimental conditions, right? Well, you can see that it's not too far away, but it's not exactly the same. And then we should start discussing the differences. First, return point memory is not perfectly obeyed. This is very clear. It is perfectly obeyed in the simulations, not in the experiments. There is a bit of crossing here. Second, the cycle is a bit tilted up, especially at these lower values of the saturation, right? We believe that the reason for that discrepancy, which is not too large, is the fact that here we are driving a viscous oil, a very viscous oil, 50 megapascals per second. And in the course of avalanches of Haynes jams, even though the driving is quasi-static, the motion is very fast. So in those Haynes jams, there is viscous dissipation. Unavoidably, there is viscous dissipation. And this is not accounted for by this model here, which are only the mechanical equilibrium configurations of the system. So this would apply to an inviscid fluid, a fluid without viscosity. Viscosity does not appear anywhere, while in our case, we have viscous dissipation. This is one of the objectives for the future years to deal with that problem. Now, just to convince you that the return point memory experimentally it's close to be satisfied, I ask you to pay attention to this point in which two different imbibition drainage cycles have been performed. One is the main one here, the other is through all this complicated excursion here, and you can see how the two interfaces at that point are nearly the same. This is pretty amazing to my understanding because this is about 20 centimeters wide, so it's complicated to have that reproducibility. Okay. This is showing that there is return point memory at microscopic scales. Now, in the 5 minutes, maybe, that I have, I will try to explain you that return point memory is not just an interesting curiosity, but it's something that can have applications. And in our upscaling problem, it has the application of allowing us to compute energy dissipation. Usually, you would compute energy dissipation just from the area of the hysteresis cycle. This is well known by everyone, that the hysteresis cycle encloses an area that is the energy lost in the irreversible cycle, right? But then you are limited to cyclic excursions. Could you do better? Could you go step by step in computing the energy dissipation instead of just having to do closed cycles? Yes, you can. That's the answer. You have to distinguish between isons. This is the nomenclature in hydrology. In isons, the system is trapped in a metastable two-phase configuration, and what the external pressure does is just to move the point a little bit by raising, for instance, in imbibition the pressure, until you make this state unstable. Then a rheon occurs. What is a rheon? A rheon is this sudden jump to a new metastable state. Okay. So the whole evolution is composed, if you put a magnifier glass here, of steps of isons with these jumps and rheons, these horizontal portions. Isons with these jumps and rheons. Okay. Rheons are irreversible and correspond to the large changes in saturation. Isons also involve little changes in saturation, as you can see here. Okay. So how can return point memory be helping us? We know we have a Hamiltonian for the problem, okay, for the disorder system. We do thermodynamics. We do a Legendre transform so that we remove the pressure term from the Hamiltonian. We don't want this external field for the internal energy. We remove the external field, and then we have the internal energy of the system. And what is interesting is that this internal energy is an state function, because we know that in cyclic trajectories, U that depends only on h of x will recover its original value. And this is the definition of a state function, right? So because h of x recovers its original microstructure, its original configuration, U will be a state function, a thermodynamic state function. Okay. Then to compute the applied work is easy. The applied work is the force times the displacement, so we compute it in the usual way. We just subtract. There is no thermal contributions here, so no need of talking about entropy. We just have the dissipated energy as the difference between the energy stored in the system and the energy applied to the system. Okay? This is the energy stored elastically in the system. This is the energy applied to the system mechanically. And now we can do that for each elementary step. So we can compute the energy dissipated. Okay. The first thing we obtain is that the total area is the total energy dissipated. We can compare the experiment and the simulations, and we get an 18% disagreement, which we attribute, as I said, to viscous dissipation. Okay. Now, we can play with the model now and find a few things. First, this is the ratio of energy dissipation in one Haynes jump compared to the work needed to produce it. Okay? And it turns out that these values are larger than 1. So it means that they can dissipate more energy than you put in an individual jump, because there was energy stored in the system, and you can release part of it in a Haynes jump, as shown here in those distributions. Okay? The other interesting thing is that this is for two different statistical distributions of the disorder. The other interesting thing is that the dissipation is not proportional to the size of the Haynes jump. One could naively think that the dissipation is just proportional to the size. Okay, it is not. It is not, especially for the smaller sizes, as you can see here. This is in log-log scale, so this is magnifying this part, and you see that this departs from a linear behavior very clearly, okay? So dissipated energy and avalanche sizes are not proportional, okay? And well, gravity stabilizes, so it's limiting hysteresis and dissipation. So the bond number increases to the right, and this is limiting dissipation. And with that, I will finish. I would have liked to talk about this, which is the last thing we have done. It's still under revision. It involves Marcel, who is sitting here, and Mikita Chubinsky, who is a postdoc in Coventry, but I'm afraid I don't have the time to go with that. Okay, so I will jump directly to the conclusions or the summary, if you want. There was still more things, but this is the summary. Essentially, it reviews what I've been saying, so I think there is no need of reading it again. You can read it. I acknowledge the funding that supported this research, and I thank you very much for your attention.
Yes, time for questions.
Really nice talk, thanks.
Thank you.
But it's possible to, by making your patches more round, to reduce the sharpness of the avalanches and then getting better memory effects?
We did not agree on that question, but it's very good that you put it, because then you give me the opportunity to go back in my slides. I promise we did not agree that, but actually this is where Marcel was involved, okay? Indeed, we figure out that this three equilibrium, let me go in still a bit backwards here. So because we are using these sharp-edged defects, we always have three metastable equilibria. But as you well say, this also could happen with that sort of profile, okay, that you have three metastable equilibria for that line, for instance. But of course, if you change the properties of your fluids or you change the profile of your defect, you can indeed get to that situation. So you can play with it, and this should be reversible at both sides, right? So this we call a weak constriction, after Dejean, who used this terminology for the first time. So you can have weak defects and strong defects. Strong defects are hysteretic in nature, and weak defects are non-hysteretic. I warn you that it does not only depend on the profile of the defect, it also depends on the slope of those lines, which on its turn depends on the viscosity of the liquid, the inclination of the cell, etc., etc. But let's imagine we set up an experiment like that. Well, Marcel did in Porlab, and this is what I will jump now to. Well, the experiment was there. This is it. So you see, this is the profile of the defect seen from above, but if we saw it from a side, this defect ramps up slowly. It ramps up slowly, okay? From here to here. And we, of course, define it such that it had to be reversible. And it is, as you can see. Here, there are the two curves in division and drainage superimposed, one on top of each other. This is the interface profile, okay? This is done in microfluidics setting. And you imbibe this, you drain it, and you do not produce any dissipation. And then the new idea here was that even though you could have weak not hysteretic defects, if you put two of those close enough, maybe they would become strong. Two together is more than two individuals, right? So yeah, this is what happens. So you put them together, the two of them are weak, non-hysteretic, but together they are hysteretic, as you can see. And the closer you put them, the more hysteretic they are. Okay. And this we could also analyze theoretically and find the threshold for that to happen. Okay. So the conclusion is, you don't really need to have very sharp constrictions or expansions. Cooperative effects can make the job for you. the job of producing a pressure saturation hysteresis cycle. This is the message. Is this answering your question?
Any other questions? Okay, maybe I'll just ask one. So you told that this effect of gravity is quite important for this problem. Now this fluid, gravity can restrict the fluid or help the fluid to flow. So if you change the angle on the other side, maybe there is still gravitational effect. But what do you comment on that? Like,
we didn't agree on that question, but, but this is important, of course. All I explained is about quasi-static driving, right? So you just look for the equilibrium states. What if you drive the fluid at finite driving rate? Then is when you need gravity, really. Because as you well know, in a Hilly-Shaw cell, two-phase displacements may relatively easily undergo the Safman-Taylor instability. So this is a morphological instability in which when you push a more viscous fluid with a less viscous fluid, the interface develops fingers. And it develops fingers very quickly. You cannot avoid that. Okay. While the reverse displacement, the more viscous pushing the less viscous fluid, is totally stable and will keep the interface flat in a rectangular geometry, right? Okay. Now, in our case, we have to tilt the cell to avoid the Safman-Taylor instability during drainage. This is exactly what happens. You see, we tilt with that angle, and this angle restricts, as you well said, the possibility of having viscous fingers, because it acts as an extra damping term to interfacial perturbations. And if you remember several transparencies before, the velocity term in the force balance equation and the applied pressure term were equivalent. They were both linear to the interfacial displacement. So actually you can replace velocity with pressure and pressure with velocity, okay? And I'm saying, velocity with the hydrostatic pressure. I'm referring to the term proportional to GE, to this effective gravity, right? So by imposing gravity is like adding a negative velocity to the system. And with this you hinder the Safman-Taylor instability, which we don't want to have here, because it would interact with a problem of capillarity that is the one we are interested in. We are not here interested in the viscous fingering instability. And this is summarized in this plot, you see. These are actual experimental data through a single constriction, but now at finite driving rate. The positive driving rate is imbibition, the negative driving rate is drainage, because again it's silicone oil displacing air, okay? So when you drive at positive velocity silicone oil, this is perfectly stable, but the new concept here is that the interface becomes more and more stable. So the fastest you drive the fluid, the more you stabilize the interface. So the deformation of the interface is smaller and smaller, even though the defect is the same. The constriction is always the same. While if you go to negative velocities, the interface becomes very ductile, let's call it like that, okay? Very deformable. And you can see it here. It becomes very, very deformable. The amplitude of deformations are enormous, up to the point in which you cannot control this anymore. And this is the Safman-Taylor instability. The Safman-Taylor instability in the linear approximation takes place when the capillary number equates the minus bone number. This is velocity dependent, this is gravity dependent. And at that point, then you have the divergence. In experiments, the divergence occurs before because of non-linearities. Thank you for your question.
maybe another, or Okay, so if not, then let's thank Jordi and all other speakers of this session. So this concludes the morning session. So lunch will be served at the same place. We will meet here at 2 o'clock for the next session. Thank you.